Okay, so I'm starting to do MATLAB demonstration of some of the aspects discussed in the first part of our course, which is 21B of the course on mathematical methods for signal processing. My standard setting, which I will use later on, is that I'm displaying signals or using signals of length n for n equals 480 with lattice constants a and b. But before doing this, let me come back to the first experiment that we had, and maybe I'm choosing just windows of length, I don't know, 50 or yeah, let's take 64. So let's say mu is a measure which is zeros of size 164, so I'm 64. So I'm using a harmless vector, and I'm producing, well, maybe first I should say that of course this is a function on the unit roots of order n. Now we have to understand that these unit roots of order n, they are forming a group, and this group has a zero element. And so in the normal way you would say you are having a function living on this cylinder, and but unfortunately the stem cell command might not work here, but let's see what we can do. And this measure would have would correspond to the Dirac at 0. So 0 is the first element in the list of elements, and we are going through the unit circle from 1 to omega squared. So the mathematical positive side sends until you reach the element which is omega to the -1, which is the conjugate of omega, which is the same as omega to the power 64. So maybe, yeah, I don't have to show it directly. But now I want to take a slight perturbation and I take the second component to be, I don't know, maybe 0.8 or so. So it's clear that the L1 norm of the different, sorry, I didn't write mu at 0, that's the unit vector, is 1. So I have a delta at 0, and then a minus delta, and maybe I take a minus, no, it's no problem. And we take another Dirac measure at 0.8. Now, if you take the difference between delta 0 and this measure, it's exactly the contribution that you have at position 2. And therefore, we can expect that everything works, so we can compute the integral. And I'm just saying, well, if there is a convolution inverse, we can do the inversion on the Fourier transform side. So I'm doing, I mean, maybe I type what I'm doing here. I take ETHFei inverse Fourier transform of 1 over of FFT of mu. So we are just saying, first we take the measure to the Fourier transform side. This is now the transfer function. I was telling you that if the measure is close enough to the unit measure, then the Fourier transform will be close enough to 1, at least it will stay away from the 0. So my 1 over command is a command which is a harmless modification of the pointwise inverse, which I think we can also do later on. And it avoids the problem that if you have a 0, that there is no inverse. So the 1 over command takes the pointwise inverse at all the points where you're far away from 0. So up to some threshold, you are putting the inverse. We are far away from 0, but that's not the problem. And so I'm taking the inverse Fourier transform. Now, maybe I'm just doing this, and then I would like to look at that new measure, new, and want to see how it looks like. So if I run the command, I hope it will work. The format will be fine. And of course, the difference is, yeah, it's very nice. So make it a little bit smaller. The difference between the original delta and this is minus 0.8 times the Dirac at 1. So if you take the convolution powers of 2, you have 0.8 times Dirac at 0 plus with alternating sign. And then you'd have the powers of this here. You see this is an exponential decay that you have here. So it's not going to 0, but everything is fine. Now, just to show you that if you would take 0.9, and then I would try to say that I'm taking the inverse in the naive sense, ones of length 164 pointwise divided by the Fourier transform. Sorry, that was not good. Run command is here. So then you should see the same thing, except that now the difference is even bigger and the decay is not as big. So you're further away from the delta, so you have less control on the norm of this, and it's an alternating sign. Now, last change, if I would put a minus here, of course the difference would be more or less the same in our case, and it would be decay. Okay, so it's like this. Now, I'm not sure if this works, but I would like to show you this as a function on the cylinder. Yeah, maybe another trick is maybe we do a plot of nu first. So after this stem command, we should see a complex curve. Okay, well, it understands here that you're having a real signal, but normally I would say I very often in computations I would say we should do a plot of the real part, because computations of forward and inverse Fourier transform may result in a tiny spurious imaginary part. And then the plot commander would say, oh, we have to plot in the complex plane, and you would see terrible things. So that's one of the reasons why I want to show this. But then I would try to do stencil, also the same thing here. That's our special command that tries to show the same function as, tries to do it, but I think, yeah. Oh yeah, here it is. Okay, perfect. So the only thing is, I think, the idea of moving it around, which you can do in a normal representation, is not working. But you also see that you have the delta at 0 and an exponential decay here, and it goes to 0, but it's a periodic function, of course. And if you take other discrete measures, if the total sum of the convolution is going like this, everything is fine. And so I'm only adding one more thing here. Maybe this is my very often used also private command of compare for me the spectrum of the function or our measure and its Fourier transform. So you should see, in this case, a harmless display of both the function and the original one. Yeah, here it is. And so this is the difference of two Dirac measures. The Fourier transform here is because our amplitude was 0.9, so it's not touching 0, because you have to think that the blue part is the real part and the red part is the imaginary part. But it's very close to 0, and that's why the Fourier transform, which we have seen is an exponential decaying curve, has a Fourier transform, or Fourier coefficients in this case, which are not so nice, but they are okay. They are still representing a measure. Now, I would like to go further down. It's too big, so sorry. Let me do a section break. Okay, so the next thing that I would like to tell you, yeah, maybe something that fits here because we have this pi command. If I would do stem cell, so the cylinder of a Henning window. A Henning window is one of the standard windows people would use to avoid the problem of I should do the section command to get rid of the jumps that you have at the end if you put things together. So here you see the exponential function, for example, has a jump at 0. It's going from 0 practically to 1 or to whatever it is. And now takes a little bit too long. So the Henning window is one of those windows which actually I was very surprised when I saw this stem plot, because what you could see is it's just here. It's a little bit higher and I typed it in the wrong place. It is just what you get if you cut the cylinder by a plane, and this plane is made such that it's, make it a little bit smaller, such that you're having, yeah, maybe it's better like this, so that you're getting cutting a cylinder such that it touches 0. This is important because whatever part of a one-dimensional signal you have, the tails might not fit. So if you periodize it, you have a problem with the jump which is not here in the signal. But on the other hand, I mean, we all know that this kind of cosine type function is quite smooth or so. And so in reality, a Henning window is nothing else but the graph, or the graph of a Henning window is nothing else but if you take a cylinder, you cut it with a plane touching here and having amplitude height 1 here, and the values that you get, they are exactly constituting the Henning window. So now I try to use another. So now I hope it's better with section break. So now I would like to demonstrate the command or the Gibbs phenomenon a little bit. No, it's not good. Now once more, section break. I hope now it's better. Okay, so how do we demonstrate the phenomenon? Maybe I'm using again this size n, and I would say I take a rectangular filter, which is in my terminology a symmetric filter of size n, and I don't know, 0.80 is the thing, so maybe we take 80. So what does it mean that I'm having a function which has a maximal deviation from the center? I mean, the stem command is a little bit too slow, but maybe I'm to the ordinary stem command, the centered stem command of this thing. So this is something where that should work fast. It's a rectangular function, and it has from the coordinate number 1 until 81, which is 80 from to the right of this, and it's having 80 coordinates to the left. So this, if you want to check it, or here you have, no, you don't see it, you can check, is it true that the sum of these ones is adding up? It's not enter, it's here. It should be 161, of course. And here you see it's 161. Okay, now we can just for convenience and because I'm lazy, let's say we're trying to do a partial sum also of this rectangular window, but with the same number of frequencies on the Fourier transform side. So maybe I call the filtered rectangular function is, I know it's to be real valued, so therefore I can say if there's an imaginary part, I throw away only almost nothing, so to say. And so I'm saying we have to go to the Fourier transform domain of my filter. It's FLT. Then I localize it with the other copy of the filter, which means this here. And then I'm going back. So I'm taking the IFFT of this localized version of the spectrum. And then I would like to see, plot C, this filtered filter. Oh, sorry, I have to run it. So we should see, yeah, exactly what I hope was wanted to show to you. We had the filter which was going here from minus 80 to plus 80. The partial sum is doing some overshoot, so it's not a kernel which is non-negative because it's the sinc kernel essentially. And so maybe I'm showing you also the F to speak the filter and the filtered filter. Or maybe if we think of a filter, we should say it's FFT of the filter. Then we are having, sorry, we have it on the right, on the Fourier transform side. So hopefully, I'm not sure if I think I was by mistake pressing the run button. So redoing everything. But the main point is that the sinc function, and here we have a compressed sinc function. So kind of what if I would take a bigger window, if my window on the time frequency side would not stop at 80, but stop at frequency 100 or 150 or so. Well, then you will see more narrow object here. It would have this finer oscillations on a bigger part of the plateau. It would be resemble constant 1 much better. And here you see what happens. On the Fourier side, we have a rectangular function. This is our filter, our multiplication scheme, because if you would change the width here, the oscillations would be finer, but the height of this overshoot or the height of the undershoot, both of them are equal. They're about 9%. So the deviation of between maximum and minimum is like 18% of the height of the jump that you have. And why is it like that? Because the sinc function has this bad property or so. So of course, we could try to do the same thing with the triangular function. Let's maybe, let's try to see what would be the triangular function, the corresponding, maybe I'm saying filt2 is the convolution of the filter with itself. So it's doing the Fourier transform of the filter pointwise squared. So I'm convolving it by itself. And, oh, sorry, I'm in the wrong window. I have to show it to in a live window. Sorry, I was jumping into a local window. Okay, yeah, do another section break. Huh. Now I have to retype it, sorry. No, it's here. Filt2 is FFT of just to make sure that I have a real valued signal. Let me run once more this section and I hope we will see it. I mean, it should, yeah, it's clearly just a triangular function or so. So if you're saying what is the filtered thing that you get with this triangular function, so it's we go for enforce real valuedness. So then we have the real valued filter FFT. So we take our frequency domain, but then instead of multiplying it with the filter, so cutting out frequencies, we do a Caesar summation, which we're multiplying with filter 2. But actually everything is happening now on the Fourier transform side. So we take the inverse Fourier transform of what we get after multiplying on the Fourier transform side with the triangular function. And I think it's the best way to understand or to see the difference is, I have a problem with the bar here, yeah, okay, is to compare now this original simple cutoff with the new one and see what we can observe. Yeah, here it is. Okay, so I think this is a kind of an explanation or an interpretation of what I was trying to explain in the beginning of in the first part of the session, that if you're doing a filter with something which doesn't have a positive Fourier transform, we've seen it was the sinc function, then you get something not so nice. If, however, you're using a triangular function, and you see, despite the fact that we are ignoring already quite a few, we are not fully reproducing low frequencies fully. The triangular function is already damping anything which has coefficients larger, let's say frequencies 30 is already damped a little bit, but still the approximation is much better. And whereas the original function has a maximum and a minimum, these smoothed versions are much better. So the moral of the story is elements from a zero, or in practical thinking, localized convolution kernels are much better for approximation or so. Now I'm trying to jump back to this Gabor setting. It's nonsense. Okay, I try to do the new instruction. Section break, yeah. So, and I'll make it a bit smaller again, hopefully. Okay, so the story was that if you give me any lattice, and I would like to tell you a little bit about the lattices and the frame operator. This is something that we have to discuss in the next session more carefully or so. So I'm saying, if you're giving me a lattice with lattice constants A and B, this is what we had already before. We create a Gabor family, which is a family, for me, a family of row vectors, which has 720 elements. So the redundancy is n divided by A times B. Actually, it's n squared. That's the number of, no, it's n compared to the number of points, and they are of the form n over A times n over B, and that's the quotient is this. So if I run this section, you should see that the redundancy, what's typo? Okay, that was destroyed a little bit. I'm sorry, but this was producing an error. So I should go here and run the section here. I'm in the wrong session again. Yeah, so here at least you see, we are now in a situation that we have 720 row vectors. All of them are labeled, sit according to some point, and the points are more or less some multiples of A in the time direction, multiples of B in the frequency direction, and we are going down in the matrix to get higher frequencies. And this is 720 is 3 over 2 times 480 or so. Now, the claim that I was making is that there's a dual window, which I call GD, which That's the kind of in-between story, which I can compute in a very, very efficient way. And we would like to compare it with the original one. This is one of the things that we should do. And what you can see here is the original one is a Gauss function. So when you compare it against the normalized Fourier transform, you see the same Gauss function. So that was the reasoning behind our choice of the discrete Gauss function. Also, this has to be discussed later on, but I hope, yeah. Whereas the dual window has two typical features. In one case, it's having a damping, so it's the like a Gauss function, but here it looks like an inverse of a Gauss function. Or the other thing is that you have side lobes. And now, of course, we can play around with other situations. So I would like to show you other windows. So what if you're computing the dual Gabor window? That's a kind of strange name, but okay. For something which is a little bit more critical, sorry, 2020, yeah, 2020. Or you take something which is less critical, so more redundant, so more in the spirit of my presentation that I was saying, if the lattice is fine enough, I don't know, maybe I take 6 and 6. So what is the redundancy of my second example? So maybe I'm checking the two redundancies is n over 400 or n over 36. Now we run this experiment. And of course, the redundancy of the first case is just 20%, I would say, or multiplicatively a factor of 1.2. We have 20% more lattice points. Or in the other case, it's a huge redundancy in some sense. You have to store 13 or more than 13 times 500 coefficients just in order to store a signal which has about 500 coefficients. On the other hand, what you see here is that the dual window is not so very nice here. And so what you can also do is, that's another command, we can look at the spectrogram. So if I say comp STF, it's a command that says I am computing now the spectrogram of these two dual windows. Each of them describes essentially how well concentrated in the time frequency plane my function is. So here, again, you will see the spectrogram of the first dual window and of the second dual window. So instead of having a time, the frequency representation, we have a time frequency representation. And I hope it doesn't take too long. Yeah, here you're showing up. You can zoom in, maybe. Yeah, I'm not doing it. I think it's a bit slow, but yeah. So what you see here is on the left-hand side. Maybe I try to zoom once more. I think, yeah, no, there's a limitation of the zoom on the screen. So here you see everything is a little bit wider or so, whereas this is more or less a you can compare it with the normalized Gauss function. So what you can observe, and that's really an observation coming from experiments. So I'm doing another section break or so. I'm saying, well, let's compare in the norm. What is the original Gabor window with the dual Gabor window, which you would get by using 6 and 6? We've seen that this means we have about a redundancy of 13. And what is quite clear is the more points you take, the smaller the dual window will be, because And you see here, it would not be a problem to take the norm. Maybe I'm saying I'm taking the norm of G minus 1333 times the no, I'm saying, sorry, the computed correct sorry, the correct, yeah, so I'll do it in this way. If I take the dual window multiply, so it's G66, I know the redundancy, so if I multiply that dual window, so I rescale it and I compare it with the size of the original one. I think that's what we would expect to be small after this. And you find out it's, for practical reasons, it's essentially the same. So what I'm saying is that if we take the proof that I did at the end of the last session, and you just insert and say, I don't do any changes, and all these factors that we get are just the samples of the original function, then we can already get a very good, I'm not sure if it was running. Okay, I see. The first one is the comp norm command with 10 to the minus 9, and the other one is that if you would just, maybe you could also take it over here. So I'm dividing by this, or I'm saying multiply. I'm dividing by the redundancy, which in my case is 6 by 6 divided by n. So maybe that's even better. And they're running it again, so I should look, yeah, okay. So you see, it's very easy to just recover in the spirit of a Gabor sum from the short-time Fourier transform, because I have only to do a mild modification. Now, another thing which is explaining you a little bit that you have to be careful with the critical lattice. So now I'm trying to take Gabor dual, or maybe GD critical is Gabor dual. I'm not sure even if it's convergent, but G 20 and 24. We all know that this is the product is n, and I would like to show this critical dual to you. And let's see if it is working. But what you expect, yeah, here it is to the right. I didn't open a subplot. It's a guy which is very extremely badly concentrated or so. If you do this for larger n, then you would expect that it's maybe even a spike that's not fully represented. Now, Guido Janssen from Eindhoven has looked at these things mathematically. He found out, well, it is an L infinity function, so it's a function which is essentially bounded, so it's not going to infinity, but it's decaying so poorly that it's not in L2, it's definitely not in L1, but it's not even in any other LP spaces. So when you make P large, the LP space is getting more and more similar to L infinity. So it's just bounded, but barely summable in any other way. Now, I could say, well, if I would change the role of analysis and synthesis window, I would expect that I can represent everything, reconstruct, and use this critical window as a building block. And that would require to do the rank of this family of functions. These are n functions, so they could be a basis for the space of functions, of signals of lengths 480. So I'm using this dual critical that we just have seen, but with lattice constants A24. That's what is supposed to be a generating system. And now I want to check. Okay, that was an error typo. GD critical, of course. The typo. And here is the answer. No. Oh yeah, of course I should display it. I should not just compute it, I should display it. And so it should pop up somewhere. Yeah. And what you see here is what I was hoping for in the sense of a demonstration. It's not a demonstration effect. It's really showing you that I get n-1. So you may ask, why didn't you get 480 or so? And this has a lot to do with what is called the Sag transform, but this is a little bit far away, so I think it's better to stop the MATLAB demonstration, maybe clean up the MATLAB file and share it with you, and finish today's session at this point. So thank you very much, and I will close the session now.